Hydrogen was seen, at least until a few years ago, as a feasible solution for a carbon-free future. Because its use does not pollute the atmosphere, the reaction product is water. That's why hydrogen was supposed to replace oil and gas. It was hoped that in a planet-friendly future we would have hydrogen-powered cars, planes, and ships. It was even hoped that home heating and cooking would also be done with hydrogen. Look at what Jules Verne wrote in The Mysterious Island. I believe that water will one day be used as fuel, that the hydrogen and oxygen that compose it, used separately or together, will provide an inexhaustible source of heat and light, of an intensity that coal cannot match. Jules Verne's dream seems not to have come true. Sure, we have electric cars on the roads, but too few hydrogen cars. Almost none, you could say. Does this mean hydrogen has no future? Let's clarify this in this section. In 2 episodes, let's see what hydrogen is, understand what its problems are, and why it hasn't managed to gain more traction in transportation. At the same time, let's also consider the other branches of the economy so we can have as realistic a view as possible of the whole situation. Last but not least, we will also address the issue of hydrogen use in Romania. Hydrogen is the most abundant fuel in the universe. The Big Bang gave it to us for free, right from the beginning of the universe. Why do I call it a fuel? Because it powers all the stars in the sky. With just 1 kilogram of hydrogen, the sun produces 26.5 megawatt hours of energy. That's enough to power a city like Râmnicu Vâlcea for a day. Ideally, we would capture hydrogen from space and fuse it, copying the process from the stars here on Earth or even in space. But that's still hundreds of years away. For now, we're trying to gather rarer hydrogen isotopes here on Earth to fuse them. But even that takes decades to do on an industrial scale. Ordinary hydrogen on Earth is mostly found in water molecules, together with oxygen, and in hydrocarbons, together with carbon. Let's forget about fusion and see what we can do with this hydrogen. For example, liquid hydrogen is used as an energy source and fuel in rocket propulsion, where mixed with liquid oxygen, it generates a chemical reaction powerful enough to send the rocket into space. The energy released from hydrogen is chemical, and very importantly, the reaction product is water, which does not pollute. Why is hydrogen used in rockets? Because it is very reactive, as it is the first element in the periodic table and the lightest, being made up of only 1 proton and 1 electron. Unfortunately, precisely because of this reactivity, we will only find a few free hydrogen atoms on Earth as they are found in space. Hydrogen atoms are already found on Earth combined in molecules such as water and hydrocarbons like methane. Notice something very important. We don't have simple atomic hydrogen available like the stars do. On Earth, hydrogen is already bound in molecules. That's why, in order to use it, we first have to extract it from molecules, which means we need to spend energy for that, and money, of course. Secondly, let's say we extract hydrogen from the water molecule using energy E. But then we use it in rocket engines or other engines to produce energy by recombining it with the same oxygen from which it was separated. What energy do we get if there are no losses along the way? It's still energy E. That is, the energy we get is the same energy we used at the beginning to extract the hydrogen from the water molecule. The conclusion: through these chemical reactions, we don't get any extra energy. In fact, we always lose energy because the efficiency is always less than 1. For example, if we separate hydrogen from water through water electrolysis and then combine it back with oxygen in the fuel cells of cars, the efficiency is 30 to 40%. We lost about 60 to 70% of the energy in the process. That's where the golden rule of a hydrogen economy comes from. In our case, hydrogen is not actually a fuel. Hydrogen is just an energy carrier. It carries energy from one place to another. Energy carrier, as it's called in English. Moreover, transferring energy using hydrogen involves a lot of energy loss. However, the initial energy has to be obtained by other methods. If hydrogen isn't a fuel, then why do we talk about hydrogen as an alternative source to fight global warming? The energy doesn't come from hydrogen. It has to come from somewhere else. Hydrogen will only transfer it from one place to another with quite low efficiency. Why is the European Union investing billions of euros in hydrogen-based technology? As we will discuss further, there are two different aspects that we need to take into account. On one hand, we already have industrial processes that need hydrogen. Fertilizers, oil refining, steel production, and so on. Whether we want it or not, we have to produce that hydrogen. Whether we do it by burning methane reforming with the associated carbon dioxide emissions. Whether we do it by separating it from water through electrolysis with zero carbon dioxide emissions. If we produce hydrogen using this second method, we can use it elsewhere, for example in transportation. We would have environmentally friendly transportation, so let's take a closer look at the methods used to produce hydrogen, of course using energy from elsewhere. Depending on the energy source used to produce hydrogen and its impact on the environment, the methods are currently classified by colors. One of the methods for hydrogen production is mixing methane with steam at high temperatures and pressures. In this way, methane breaks down into hydrogen and carbon dioxide. The hydrogen is in the cylinder under pressure, or it is sent through pipelines where it is needed, and the carbon dioxide is released into the atmosphere. The hydrogen produced this way is called gray because the carbon dioxide released into the atmosphere contributes to global warming. Basically, instead of burning methane directly like we do on the stove, we do it in a controlled way. This way we can recover the hydrogen. Because a fossil fuel is burned, in this case methane, and carbon dioxide is released into the atmosphere, the method is polluting, even though it is cheaper compared to other methods. As I mentioned, gray hydrogen is produced today in large quantities for industrial processes, contributing about 2% to global warming. Then we have blue hydrogen. It is also obtained by burning methane, the kind extracted from the ground. But now the carbon dioxide is not released entirely into the atmosphere. Instead, it is partially captured and then stored and deposited, mostly in gases and liquids. In other words, it would only partially contribute to global warming. At first, it was estimated that this method captures about 70 to 80% of the carbon dioxide generated by combustion. This value is still unclear. Then there's green hydrogen. It is mainly produced by water electrolysis, which means breaking down water molecules into hydrogen and oxygen by passing electricity through water. If the electricity needed for electrolysis is produced separately from renewable energy sources such as wind, hydropower, or solar, we say that the hydrogen produced this way is green or renewable. Because the entire process does not generate carbon dioxide and does not contribute to global warming. We are not discussing here the manufacture of equipment such as electrolyzers, which themselves can emit carbon dioxide during the manufacturing process. Green hydrogen is currently the most sustainable form of hydrogen, but also the most expensive. We need wind farms or solar farms for clean energy, and in addition, we also need to use electrolysis facilities at the industrial level to extract hydrogen from water molecules, thus converting part of the electrical energy into the chemical energy of hydrogen. We will come back to this. Climate change. Climate change is no joke. Global warming is now accepted by the scientific community just as the Big Bang is accepted. We discussed the source of the problems in a dedicated series. The burning of fossil fuels, which has accelerated over the past century. This has increased the concentration of carbon dioxide in the atmosphere and contributed to an amplified greenhouse effect. I called it the Blabooma effect. To curb the rise in average temperature, we need to reduce the proportion of carbon dioxide in the atmosphere which has been amplified, and to curb the rise, we need to reduce the proportion of the amount, leading to an amplified greenhouse effect. To curb the rise in temperature, we need to reduce the proportion of carbon dioxide in the atmosphere, which leads to an amplified greenhouse effect. To curb the rise in average temperature, we need to reduce the amount of carbon dioxide, which amplifies the greenhouse effect. To slow temperature rise, we must reduce carbon dioxide, which amplifies warming. This means that by then, most of the energy sources based on fossil fuels, coal, oil, and gas, must be replaced with renewable sources within the territory of the European Union. This can be seen in this chart. On the vertical axis is the reduction of sources based on fossil fuels. Compared to 1990 and 2017, there were 20 fewer energy sources based on fossil fuels. In 2050, there should be 100 fewer, meaning that fossil fuels would not be used at all. Hydrogen should replace 20 of today's fossil fuels. The funny thing is that, to a large extent, hydrogen has to replace itself. Why? Because already in the global industry, almost 90 million tons of hydrogen are produced every year. That hydrogen is used in fertilizer. This is for oil or steel production. This hydrogen, however, is classified as a fossil fuel because it is produced by reforming methane, so by using fossil fuel. The contribution of these industrial processes to global warming is estimated to be around 2%. That's why this hydrogen is called gray hydrogen. If we want climate neutrality, we need to replace the process of producing this industrial gray hydrogen, which uses methane combustion, with one that uses green energy like photovoltaic panels, wind power, and electrolysis. We will have green hydrogen because its production does not involve fossil fuels. Once we replace the entire industrial hydrogen production process, the 90 million tons per year from gray hydrogen to green hydrogen, we can think about the next step. Using the acquired technology, such as photovoltaic panels and electrolyzers, to produce green hydrogen and use it as an energy source for other things, cars, airplanes, heating homes, and so on. Look at what the forecast for global demand for green hydrogen produced by renewable energy look like. In 2050, this would be somewhere between 125 and 600 million tons per year. Part of it should replace the gray hydrogen used today in industrial processes. Alone, it won't be all 90 million tons. The rest would be green hydrogen used in other areas, cars, residential homes, and so on. On the right side of the chart, you can see how, over time, the demand for gray hydrogen needs to decrease from 90 million tons to zero, if possible. How much green hydrogen is available today? We check the chart's bottom left. The number is so small that you can't even see it. A figure I found on the internet is, it's somewhere below 1 million tons per year. To clarify, we need to boost production of green hydrogen, photovoltaic panels, and wind turbines. In electrolyzers, by 2050 worldwide, from under 1 million tons per year to over 100 million tons per year, even 600. That means even more than 600 times as much. In the European Union, together with Great Britain, somewhere between 50 and 100 million tons of green hydrogen should be produced in 2050, as you can see in this chart. To reach these very ambitious targets, the European Union has made a plan. It's called REPowerEU. With it, the European Union aims to reach, by 2030, a production of 10 million tons of hydrogen per year on European territory. Green hydrogen, and respectively to import another 10 million tons of green hydrogen per year by the year 2020. Let's get an idea. In 2022, the production of green hydrogen was estimated somewhere between 0.2 and 0.4 million tons per year. The increase would then be more than 20 times higher. As we can see, the targets are very ambitious. In addition, they are also costly. It makes sense not to forget that this increase necessarily comes with an additional contribution of renewable energy capacities, without which green hydrogen could not be produced. Is this the plan of a realistic European? Let's see. There is an area today where gray hydrogen is heavily used: industry. You can see this at the top of the chart, where it says unavoidable, meaning this gray hydrogen needs to be replaced with green hydrogen. Industries like steelmaking, chemical manufacturing, and refining are major consumers of hydrogen. Another major consumer will be the steel industry, once the production process changes to one where iron ore is turned into metallic iron without being melted. Hydrogen is also essential in the production of ammonia for fertilizers and methanol, which are vital for global agriculture and chemical industries. At the bottom, we also see industries where the use of hydrogen is being attempted, such as mobility and heating or electricity generation. We see in this chart another prediction of the global demand for clean hydrogen. As I said, industry uses about 90 million tons of hydrogen annually, shown in dark blue. Currently, 99% of industrial hydrogen is gray. It contributes to carbon emissions and global warming by about 2%, and it should be substantially replaced with green hydrogen. The rest, up to around 400 million tons, are desired applications for green hydrogen. I said clean hydrogen because it could in principle also be blue hydrogen, meaning hydrogen produced by burning methane, but without the reaction products, especially carbon dioxide, reaching the atmosphere. They would be stored. However, recently, in 2021, an article by the American researcher Robert Howard caused a stir. He detailed all the chemical processes that take place in the production of blue hydrogen. To his surprise, he discovered that, in practice, the total contribution of blue hydrogen to the greenhouse effect is only 10% lower than that of gray hydrogen, as shown in this graph. Methane emissions also made an important contribution, as methane is known to be a more potent greenhouse gas than carbon dioxide. I also checked the reactions following the article. It seems that other researchers consider Howard's result to be exaggerated. I don't know the truth. What I can tell you, however, is that lately there's been less talk about green hydrogen and more about clean hydrogen. That means it's somewhat accepted that, realistically speaking, perfectly green hydrogen is a dream that's harder to achieve. One of the reasons is the intermittency of its production, mainly due to the lack of electrical flexibility, which would greatly increase the price of green hydrogen. To replace gray hydrogen with green hydrogen, at least for industrial applications, we need industrial-scale electrolyzers. As I said, electrolyzers are the ones that, using electricity preferably from solar panels and wind turbines, extract hydrogen from water. Just like this battery placed in water, at its negative terminal it releases hydrogen, separated by electric currents from the water molecules. There are also other methods of producing hydrogen: photocatalytic thermolysis, catalysis, and so on, but we won't discuss them here. Electrolyzers are the most popular. Because electrolyzers are currently expensive, Western countries provide subsidies to companies. The Netherlands, for example, wants to subsidize the production of industrial electrolyzers with more than 1 billion euros for each gigawatt of electric power of the electrolyzer. That means over 1,000 euros for each unit that has an electrolysis capacity of about 1 kilogram. Two of the electrolyzer technologies are alkaline electrolyzers and proton exchange membrane electrolyzers. Alkaline electrolyzers are basically what we learned about in school, like the battery example. They use a liquid electrolyte, usually potassium hydroxide or sodium hydroxide, through which an electric current flows between two electrodes, the anode and the cathode. Hydrogen is generated at the cathode and oxygen at the anode. This is a mature and well-established technology with relatively low costs, but it requires longer startup times and works optimally only at a constant operating regime. Recently, proton exchange membrane electrolyzers have been developed. These use a solid membrane, usually a polymer, which allows only protons to pass through it. When an electric voltage is applied to the electrolyzer, the water supplied to the anode is broken down into oxygen, protons, and electrons. The electrons are released into the external electric circuit. However, the protons pass through the membrane to the cathode, where they combine with the electrons coming through the circuit to form hydrogen gas. This technology is newer, but it offers flexibility and a quick response to load variations. In 2023, the price of the alkaline electrolyzer was around 300 euros per kilowatt of electrolysis capacity, and the price of proton exchange membrane electrolyzers was about twice as high. Let's remember, however, that subsidies were over 300 euros per kilowatt, even over 1,000 euros per kilowatt in the case of the Netherlands. It's easy to see how the subsidies fully cover the costs of the electrolyzers and thus encourage manufacturers to use these subsidies. However, in some circles these subsidies are viewed critically. Why? Because it is said, by granting such advantageous subsidies, the European Union is already preferentially favoring one technology, the electrolyzers, over others. Wouldn't it be better to let the free market follow its own path and thus allow the most competitive technology to select itself? It is also said that the efficiency of electrolyzers is low. For every kilowatt hour of energy that the electrolyzer puts into green hydrogen, it consumes between 1.5 and 2.5 kilowatt hours of electricity. The efficiency of electrolyzers is estimated to be somewhere between 40 and 70% depending on the type. Today, the hydrogen used in industry is mostly gray, meaning it is produced by burning methane. Technically, this is called methane reforming. Gray hydrogen thus contributes to global warming by about 2%. The cost that the industrial sector pays for this gray hydrogen today is somewhere between €1 and €2 per kilogram. If we were to use green hydrogen instead, the production cost would be somewhere between €4 and €5 per kilogram, which is much higher. If we add transportation and storage, hydrogen reaches the pump for cars at a price of 12 to 18 euros per kilogram in France, Germany, or California. We can ask ourselves, is this additional cost worth it just to eliminate part of the source of global warming, producing gray hydrogen by burning, reforming methane? On one hand, the answer is political. Do we want to replace gray hydrogen in industrial processes that already contribute 2% to global warming? On the other hand, the pragmatic answer also depends on how the price of electricity will evolve in the future. Because that's where the energy stored in green hydrogen comes from. Hydrogen is an energy carrier, as I mentioned. In this chart, we see a prediction of how the price of hydrogen will evolve in an optimistic scenario until the year 2050. The price of gray hydrogen would increase, more taxes, difficulties in obtaining the gas, and so on. On the other hand, the price of green hydrogen could drop to almost €1 per kilogram. That is about the same as gray hydrogen costs today. It's impossible for me to say whether what we see in the chart is just wishful thinking, or if it can actually become reality, because the price evolution depends on many factors. The decrease in electricity prices, the decrease in the cost of renewables, photovoltaic panels, the decrease in electricity storage costs, the evolution of electrolysis technology, and so on. The desired cost of €1 per kilogram. It probably includes subsidies at the beginning, but if the rest of the things fall into place, it could become real. I'm not in a position to say that. Let's get an idea. The EPG report titled Clean Hydrogen in Romania. It says that based on an electricity price of €50 per megawatt hour, a reasonable, even conservative assumption for Romania in the year 2030. The levelized cost of green hydrogen will then be between 2.2 and 2.7 euros per kilogram. That's about twice as much, even though it's much earlier. In the end, let's not forget one thing. It will always be cheaper to use electricity directly than to convert it into hydrogen with energy losses along the way. This will be very important in automotive transport, as we will see in the next episode. I'll stop here with this episode. The next one will come in a few days, a week at most. We will then discuss hydrogen cars, hydrogen heating, and we will detail the situation in Romania. Until then, I am Christian Prezura. Stay cool and I wish you all the best. Goodbye.